Okay, welcome to our first project. This is the speeding project. This is the third video for the speeding project. You've already seen a documentary about Émilie de Châtelet, and that is telling you how the formula for kinetic energy was found and proven and distributed to the world. You've also seen an Australian traffic safety video. Everything in it was in kilometers per hour, so you had to convert those into miles per hour. We're now referring to that Australian public safety video, and we're going to go back through it, and we're going to answer some questions about it. So the first question is, the injuries suffered by the young woman were influenced by what two speeds? And of course, the first of those, and the things that she might immediately care about most, is the speed at which she was hit. But the thing that determined that, the speed that determined the speed she was hit at, is the speed that he was traveling when he first saw her. In other words, the fact that he was going well over the speed limit. From the second video, you know that the formula for kinetic energy is E, that is the amount of energy, just like the E in E equals mc squared. That K takes into consideration the fact that there is a constant. And that's the same K that you saw in an algebra course. That K allows you to use different units than metric units. So the K allows us to deal with miles per hour and pounds and things that we're familiar with in the United States. So K is that gasket, it takes care of the units. M is mass. Mass, of course, is the physics way of saying weight. And V is velocity. V is the speed. And K, of course, takes care of the fact that we can use different units. E could be in joules if we were metric. It could be in generic collision impact scale. E is the amount of energy that has to be dissipated when you're moving, when you're traveling. So we might say, well, what happened in that collision? There were two ways that energy was dissipated. One was with the car on the road. That is the braking in the car, the brake pads, the brake disc, the tires on the road. And the second, the one that did all the damage, was braking, actually deceleration that happened by hitting the young woman, by throwing her 6 meters, about 20 feet. That happened because the car was transferring some of its energy to her. Now go back over to those pages, and I'm just going to copy and paste these in. So in the speeding collision, this is when she was sent to the trauma ward, she was hit at about 20 miles per hour. So depending on where you rounded it, I rounded it to 2 decimal places, so 19.88 miles per hour. Now by driving the speed limit, which is in urbanized areas in Australia about 60 kilometers an hour, that was about 3 miles per hour less than he was driving. He was over the speed limit. And if he had been traveling at the speed limit, that collision, and look back again, because they go through all these numbers, would have been 3.1 miles per hour. And so you might say, what on earth accounts for such a huge difference in speed? The trauma ward versus, just arranging a settlement at the scene. That's a huge difference. And that, of course, comes from, as you know from watching the documentary on Émilie de Châtelet, that comes from the square of the velocity, the fact that the speed is squared. Now here's a quick reminder of how to deal with variation questions. So you remember this from your algebra courses. This is something that's a theme throughout them. So first off, variation means is a multiple of. So we can take that word varies and we can rewrite it as is a multiple of. And of course that tells us everything that we need to know. Is the equal sign, a multiple is our k, and of tells us to multiply. So equals k times. Equals k times is literally how varies translates, and you remember that from an algebra course. Directly means we're in the numerator, inversely or indirectly means we're in the denominator, and jointly means, hey, what you're going to hear about, multiply those together. And remember, jointly is a modifier, so if you see jointly of something and something else, that and does not mean addition, it means multiplication, that is the product. So here's our steps, and this is copied and pasted out of my algebra course. We translate to get the general equation. We substitute in the given information. We solve for k. That gives us the specific equation, specific in the sense that it is only about the units in question. You can measure things in lots of different units, and k will take all of that into consideration from the experiment that you hear about in that first step. So once you've got k, you've now in step 4 got the specific equation. You then substitute in the question and solve it, and of course state your answer. One of the things we want to remind ourselves of is our equation. So let's start by translation. It says the amount of energy in a collision, that is E for energy, varies. Remember, varies means equals k time. Directly tells us that what's coming is going to be multiplied. So that and back there, the and right here, is telling us to multiply, not add, because of the directly, with the mass. We're going to use m for mass, and the square of the velocity. So when we plug all that good stuff into our formula, we've got E equals kmv squared. Now that looks an awful lot like E equals mc squared, where c is the speed of light. That's the amount of energy in matter. The sailors on the Enterprise spelled it out on the deck because that was the first nuclear-powered aircraft carrier. Here, v is a speed still. It's the speed at which you're traveling. Both equations are true for the same reasons. Now let's look at this equation in terms of metric units. It says to translate, the amount of energy in joules released in a collision is 1/2 the mass in kilograms times the square of the velocity in meters per second. So if we're using metric measurements, this becomes really easy. The k goes away. We don't have to solve for it. It's always 1/2. That actually comes from calculus. The 1/2 comes from integrating, that is, finding all those instantaneous amounts of energy. So E equals 1/2 mv squared. If we're using metric measurements, that is kilograms and meters per second, we don't have to go through the process of finding k. Okay, let's look at an example in the units that we're familiar with, English or imperial units. It says the collision impact of an automobile varies jointly with its weight and the square of its speed. So that sounds exactly right. E equals kmv squared. So that's exactly the formula we're going to use. Then it gives us some information. We could translate that first sentence, or we could just use the fact that we already know, thanks to Emily de Châtelet, the formula for the amount of energy in motion. It now says suppose, so an experiment was performed, a 2,000-pound car traveling at 55 miles per hour has a collision impact of 6.1. So of course the first thing we're going to do is substitute all that in. So taking the place of E is 6.1. K will take care of the fact that we've got some pretty strange units, pounds and miles per hour, and some unknown units for the collision impact. We could certainly go through and work those out, but let's just call it collision impact. So that gives us our equation for k. So let's solve that for k. When we do that, we divide both sides by 2,000, and we divide both sides by 55 squared. When you put this into your calculator, just check that you got approximately what I got. We're not ever going to enter this number. We're going to leave it on our calculator screen. Our calculator is storing far more digits than it's showing to us. So it's always a good idea, and I'm sure all your math professors have told you this. Don't clear an answer and re-enter it. You'd be re-entering a much higher rounded version. So keep the more exact version in your calculator. The only reason I'm putting that up there is to make sure that you entered it into your calculator correctly using the order of operations. Now we've got a question. That last sentence is a question, and of course using k we can answer it. We want to know what E is. We've got k, so there's k, just copied and pasted. Remember, that's already on your calculator screen. The mass is now 3,000 pounds, so we're going to multiply k times 3,000, and the speed is now 65 miles per hour. Remember, that 65 needs to be squared just like the 55 was squared. That'll give us our E, our collision impact, which I rounded to 12.7798. And of course, we have to say this in words, and we say that collision impact is more than twice as great at 12.8. Notice I rounded that to 12.8 because the question gave us collision impact as 6.1 with 1 decimal place. The next question, already I'm liking the second question a little bit better. Notice that it says the amount of joules. It's asking for joules. That's telling me that this is a question that we should be able to do in metric measurements. And then I notice we've got pounds, but we've also got kilograms. I notice we've got miles per hour, but we've also got meters per second. Now, certainly you could use either of these, but if you used imperial, you'd have to convert it into joules. So we might as well just use the metric units right from the get-go. And that'll save us a lot of time. Notice we can have this problem done much quicker than the previous one because we don't need to find k. K is that 1/2 that comes to us from calculus. And so we simply plug it in. E equals 1/2, we're dealing with metric. And there's the mass in kilograms, so the 4,535. And the velocity in meters per second, 18. Remember that 18 is squared. That's why we watched the documentary on Émilie de Châtelet, and you've got that link, and you've already been through it. Let's make sure that we get the same answer when we perform this arithmetic. Misspelled joules there. 734,670 joules, so about 3/4 of a million joules. The next two questions ask us if we can compute how many times larger one thing is than another. So how many times, a question about multiplication, is solved with division. So we're going to set this up as a fraction, the larger one over the smaller one. The feet are going to cancel. Feet upstairs, feet downstairs, units cancel in the same way everything else does, essentially. So we're left with 15 divided by 5, which is 3. So we can say that the larger distance, 15 feet, is 3 times greater than 5 feet. The next question asks us to compare hours to hours. The hours are going to cancel just like the feet did in the previous problem. 87 hours over 3 hours is going to leave us with 29. So we're going to say that 87 hours is 29 times greater than 3 hours. Now, that is a preamble. It's reminding us how to solve questions that involve how many time questions. So how many times more energy? So we're talking about energy here. We've got an equation for energy. It looks like we're going to have to use the version with K because I'm seeing miles per hour here. And it's asking us how many times more energy was released in a collision at 50 miles per hour than at 35 miles per hour. So we're going to see a quotient just like in the previous two questions, a fraction, a numerator, and a denominator. In the numerator, we're going to put the amount of energy in a collision with 50 miles per hour. In the denominator, 35 miles per hour. You're going to see the k's, the m's, and then the velocities squared. So when we do that, there's the k's, the m's, and 50 squared, a k and m, and a 35 squared downstairs. Now, implicit in this question is the idea that the road conditions are the same, so k stays the same. And this is the same vehicle from one experiment to the other. It doesn't specify differently than that. So m stays the same. So, which means that this becomes a much easier question very quickly. The k's cancel, the m's cancel, and we're left with 50 squared over 35 squared. Now you could put that immediately into your calculator, but let's look at the arithmetic. 50 is 5 times 10. 35 is 5 times 7. So we can factor both of those and notice 5 squared over 5 squared. Well, the 5 squareds cancel, and we're left with 10 squared over 7 squared. 10 squared is 100. 7 squared is 49. That's really close to 50. So this is almost twice as much. Well, a little bit more than twice as much, but twice as much is certainly a good estimate. I live on a road where the speed limit is 35 miles per hour. Cars regularly go freeway speeds, and the amount of energy there is twice as much. Compare that to the traffic safety video that you saw a few minutes ago. Okay, we're going to do 2 more of these, the exact same idea, how many times more energy. So we're going to see a quotient, both miles per hour, so there's going to be a k and an m, and then of course those velocities squared. At 40 miles per hour, then 15 miles per hour. Of course the k's and the m's are going to cancel. We're assuming it's the same road conditions and the same mass of the vehicle. We're going to look at that 40 and that 15. 40 is 8 times 5. 15 is 3 times 5. 5 squared over 5 squared cancels, and we're left with 8 squared over 3 squared. 8 squared is 64. 3 squared is 9. And with a little arithmetic, we can say there was 7 times more energy in a collision at 40 miles per hour than at 15 miles per hour. A good rule of thumb, and you've probably come across this in driver training courses, is if you're hit by an automobile at 25 miles an hour, you have an 80% chance of surviving that collision. However, if you're hit at 35 miles per hour, just a tad larger, some drivers might think, that person, you only have a 20% of chance of surviving and an 80% chance that you'll be killed. So really important, those speeds. How many times more energy was released in a collision at 35 miles an hour than 25 miles per hour? Again, we're going to go through that. We're assuming the same road conditions, same mass of the vehicle. We're going to go through and factor out those 5. So 5 times 7 upstairs, 5 times 5 downstairs. The 5 squareds cancel. So we're left with 7 squared over 5 squared. These numbers are really nice. 7 squared is 49, real close to 50. And 5 squared is 25. 50 divided by 25 is 2. So this is really close to 2. Our last question gets us all the way there. It says, on a fenced-off track, an engineer applies the brakes to skid to a stop from a speed of 35 miles per hour. So we've got our velocity. The skid marks are 93 feet long. The next sentence is a question, so we use that first pair of sentences to get K, and then using K, we want to figure out how long the skid marks would have been had the engineer began to skid at 49 miles per hour. Now, notice here that we're, again, assuming that the two vehicles, or they're the same vehicle, so the mass is the same, and of course the K is the same for both of these. So we plug it into the equation. It says that the amount of energy had to be dissipated in terms of braking or skidding for 93 feet, so that's taking the place of E. Notice that there's no M because it would simply follow us through the question. We're assuming it's the same from beginning to end. The K is our first goal. We want to solve it. We've got a velocity of 35 miles per hour. Of course, that has to be squared. Rewatch the documentary on Emily de Châtelet if you need to. So we solve this for K. We put it in our calculator just to make sure that our calculator is calculating the way it should be. Now that we've got K, we can put this back into that general equation and ask the question how long the skid marks would have been. That is, what is E when K is 0.075918 and our velocity is 49 miles per hour. So again, into a calculator it goes, and out comes approximately 182.28. We say that in words, as the skid marks would have been approximately 182.28, or a quarter, feet long.